El Niño and La Niña events, collectively known as ENSO, generate profound year-to-year changes in weather patterns around the world. Using a supercomputer, we have recreated the strongest El Niño on record in late 1997 that was followed by two back-to-back La Niñas. The heart of ENSO is in the vast tropical Pacific. Much of the action occurs below the surface. To see this, we focus on a 300-metre deep slice of the ocean along the equator. A massive pool of warm water sits in the west, while in the east, cooler water extends almost to the surface. This creates a strong west-to-east slope in the depth of the warm layer. As the El Niño grows, the warm water floods eastward, displacing the cold water and flattening the base of the warm layer. As the La Niña develops, the opposite occurs. The eastern Pacific cools and the warm pool reforms in the west. This temperature contrast across the equatorial Pacific is linked to the westward blowing trade winds, with winds strengthening during a La Niña and weakening during an El Niño. To make these changes easier to see, we run the sequence again using temperature deviations instead of absolute temperatures. Reds represent warmer and blue colder than normal temperatures. Before the El Niño arrives, we see a build-up of warm water deep below the surface that moves eastward, getting shallower as it goes. Near the end of 97, this warm water breaks through to the surface, making the central and eastern Pacific much warmer than normal. As a consequence, the overlying trade winds, which normally blow from east to west, weaken. Even as the El Niño peaks, we can foresee its demise, as cool, deep water in the west moves eastward. The cool water eventually surfaces, ending the El Niño and starting a La Niña. While the surface signature of the La Niña weakens through 99, by the end of the year, cold subsurface water again rises to the surface, bringing a second La Niña. This gradually fades away, returning the Pacific to neutral conditions. By peeling away the ocean's surface, we can see how ocean currents move heat around. Here we see volumes of water that are at least 2 degrees Celsius warmer or colder than normal. Again, there is build-up of subsurface heat before the El Niño. Bursts of wind in the western Pacific trigger subsurface ocean waves that pulse the heat towards the east. We can also see how subsurface heat moves away from the tropical Pacific, poleward along the South American coast and into the Indian Ocean through the Indonesian archipelago. Heat also escapes to the atmosphere from the warm eastern waters. At the same time, cold water hundreds of metres below the surface in the west is moving eastwards. It surfaces in the central Pacific, bringing the La Niña. This shows how understanding the subsurface ocean and maintaining a reliable ocean observing network is critical for predicting ENSO months in advance and making accurate seasonal forecasts. Changes in ocean temperatures associated with ENSO profoundly changes atmospheric circulation and rainfall patterns. In this animation, areas of more rainfall are shown in white and less rainfall in pink. Tropical rainfall is tightly linked to warm sea surface temperatures. As the 97 El Niño develops, more rainfall occurs across the equator in the east, above the warmer waters. Drier conditions develop off the equator and in the west. This is why El Niños bring dry conditions to western Pacific Rim countries like Australia. As we move to a La Niña, the opposite occurs. The central equatorial Pacific becomes drier, and in the west, rainfall increases, including over Australia. ENSO has global impacts, affecting droughts, floods, bushfire, coral bleaching, and much more. Understanding how it works is key to predicting when it will hit and managing its often devastating impacts.